Hello, my name is Cal Gilroy, and I'm the Applications Development Manager for Vision Research AMETEK. Today I'm going to talk to you about image-based measurements in automotive crash testing. The outline of this talk is the following. I'm going to go through a brief introduction to high-speed imaging. I'm going to talk about the common imaging applications found in the automotive testing industry. I'm going to go through a typical crash test scenario designed for extracting measurements from that video. I'll talk about 2D and 3D measurement setups. I'll show you some example videos, and I'll be available for some comments and questions. So generally, high-speed imaging is wide-ranging. There are a number of applications where high-speed cameras are used. So to give you an idea of what frame rates are used in the various industries, just to give you a wide perspective, for looking at animal movement kinesiology, generally we use around 1,000 to 5,000 frames per second. For device drop testing, we'll use between 5,000 and 20,000 frames per second. For ballistics and aerospace, with things moving at the speed of a bullet, that's going to be between 10,000 and 100,000 frames per second. And then for things that like crack propagation and brittle material failure, that could go beyond 100,000 frames per second and upwards to 1,000,000 frames per second. Now, the automotive industry generally is between 1,000 frames per second and 10,000 frames per second, depending on what your imaging application is. Now, for typical crash tests, you'll see cameras running at around 1,000 frames per second, sometimes 2, sometimes 5,000 frames per second. We've been on tests where we looked at tire testing, accelerating deformation in a tire, around 2,000 frames per second. Looking at car seat and seatbelt testing, right around 1,000 frames per second. Inside the engine or some kind of combustion testing could be upwards of 10,000 frames per second. And then looking at glass fracture and deformation in these materials could be upwards of 100,000 frames per second. Different component testing is completely variable in terms of its frame rate, depending on what you're looking at. Battery testing in, for example, EVs are heavily tested using high-speed cameras. That could be anywhere from drop testing to failure analysis to thermal runaway in these batteries. And what we're doing with all these is essentially doing a kinematic extraction where we look at things like speed versus time. We look at displacement versus time, or even acceleration versus time. In some cases, folks are using the high-speed camera to measure the position versus time. And in this case, they are able to extract things like vibration over time as well from the video data. Here is a side view of a crash dummy tracking analysis test. So the key here is, in this case, camera positioning. You'll notice that the camera is positioned orthogonal to the event plane, the motion plane. You'll see that there is a scale in the frame here, and that scale is typically used to educate the software that's analyzing it on what is the actual physical length units per pixel in this video. And that will result in a calibrated field of view. You'll see that this scene is decorated with quad or fiducial markers throughout, indicated by the orange arrows. There are also a number of well-defined features. Software nowadays is clever enough to track both types of features. Here we see the test proceeding. And what we don't see is that this test is very carefully timed, where the camera is synchronized with other data acquisition units. It's also triggered at a key moment in time relative to the event, and there's generally a master timing for the experiment where each device, camera, any kind of data collection is occurring at the same time. Here's another look at a test where an infant dummy is placed in a car seat. As you can see, you have that marker on the head moving forward. This can be readily imported into a post-processing software. Here we have an example from the Phantom Cine Analyzer, where the Cine file was imported into this software. You can see that you can progress through the frames. You can also do automatic tracking, where we can add different objects. For example, this fiducial marker on the head, we can click the head position and very carefully select the center of that fiducial marker. We can also detect other features such as this ankle position here. Even though this is not a design marker, it could be still used to track. We can name it the head, and we can also name this the ankle. Okay, and that's saved. So what we can do now is open the auto track dialog. We can go ahead and select the auto tracking parameters. In this case, we'll do 51 by 51 for the template area for both subjects. And what we'll do is we'll go into the advanced settings, and instead of doing single pixel interpolation, we will do a 1/10 pixel processing, and we'll go ahead and we'll process the data. And whenever you do a 1/10 pixel interpolation, essentially what you're doing is you are interpolating the template in the search area in this software. And what that allows you to do is get way more detail and accuracy in your tracking measurement. It will, however, increase the processing time needed to extract that data. But in many cases, it is well worth it. As we wait for this to process, you'll notice that we have a scale bar in the upper left corner of the image where it is in inches per pixel. So in this particular case, a physical scale was used to calibrate this video. And on the very bottom of this GUI, you will see a plot where we have displacement versus time. This is where once we are done processing the video, you will see that all the data will be populated down there. So here you notice that there are a red and orange tracking position of the markers and the ankle. And you can see as we progress through the video, we have a nice displacement versus time graph. We can open that up and take a look at that here. And we can choose between X displacement, Y displacement. We also have the option to change speed, X speed, Y speed, acceleration, and so on. There are other softwares, for example, ORME signals and images, where you can do 6D measurements, where the crash dummy head can be used as a modality to get your 6 degrees of freedom type measurements. And here's a perfect example of it here. Here's an example of the same software from ORME using to get the airbag deployment analysis, where you can essentially get the edges of that airbag throughout the deployment to learn about how it deforms over time. Here we have airbag area versus time. So you can import your high-speed video into the image systems software, and you can essentially get the area as it expands per millisecond of the experiment. An emerging technique is called digital image correlation. This is a non-contact method used to measure the full field strain or displacement of dynamically deformed subjects. So here's an example of a Humvee tire rotating at high speed. If you notice, there is a speckle pattern decorated all over the front surface of the tire. And what you can do with this video is you can import that into a post-processing software and extract the full field strain from this measurement. This is a measurement from Trillion Quality Systems, where they were able to extract full field strain from this Humvee tire as it accelerated. You can also see that there are vectors also projected onto the deforming subject as well. Another interesting application is if you are studying shocks or springs. You can import that into the Dantec Dynamics software, and for example, you can do a correlation evaluation and analyze the subset facets as you undergo a compression. A more dramatic example here is we have a glass cracking experiment where as we deform or crack this glass, you can import that into your third-party software. This is at roughly 115,000 frames per second, computed with the Trillion software from GOM, and you can notice that you can see deformation of that glass versus time in really great time-resolved manner. You can also apply this technology to crash testing. This is a shot from the Correlated Solutions website. They also provide DIC software. As you can see, you can project a full field deformation and or strain map onto a vehicle as it's crashing into a particular barrier. Here we have a vibration analysis. This is from Correlated Solutions. In this, they're essentially showing how you can do an animated 3D view of a brake rotor at 2087 Hertz. So what you're looking at is essentially the operational deflection shape of that rotor during a high-speed test.